Okay, first of all, can you hear me well, everyone? Okay, so, well, thanks a lot. I would like to join the rest of the speakers in thanking the organizers for putting this wonderful workshop together and giving me the opportunity to speak here today. It's very nice and kind of humbling to see the great work that people are doing. So my work is very modest, but it kept me entertained during the pandemic, and this is the first time that I'll be able to share it. So let me start with some motivation. I guess we're all here because we're interested in quantum matter and light, and I like to think that the quantum particles, they have their own identity. So I can show the identity card of, for instance, an electron, and an electron will have, let's say, a couple of properties that would define them, right? It will have a mass, a charge, a spin. Let's say a handful of properties that encapsulate, to some extent, this identity of electrons or quarks or whatnot. Now, in condensed matter, in Bose-Einstein condensates, often we deal more with quasi-particles, right? These localized excitations. So we often hear about phonons, excitons, polarons, whatnot, right? And these two, I want to think they have their own identity. So they have also a handful of properties, an effective mass, charge, spin, and statistics. Now, within this identity, I would claim there's an intrinsic quantum identity, right? Typically encapsulated by the spin and statistics. And today I want to focus on the statistics and direct change. Now, typically when we speak about statistics of quantum particles, we have to start speaking about communism and capitalism, or bosons or fermions. Well, I think I don't have to explain what a boson or a fermion is. I will be interested, though, in the exchange properties of these particles or quasi-particles, and this sometimes encapsulated right in the commutation relations of matter. So we're told, look, if you deal with photons, these are bosons. If we deal with electrons, these are fermions, and we write down our theories and we take it from there. And there's a certain immutability on this. Also, there's this nice animation that I found online. I think it's very beautiful. So let me run it for a full period. Okay, enough. So today I want to sort of challenge this immutability in the sense of what was a bit explained in the first talk, right? So the idea is, can we turn capitalists into communists and the other way around? Or more concretely, can we manipulate and maybe even tune this quantum identity of matter in an effective way? Now, if I think how to get effective bosons out of fermions, well, we had an example of a BCS state transitioning to BEC regime, right, in which you have initially gas of fermions, and effectively, they pair up, and you get effective bosonic behavior. Now, if I think very naively, I would say that that's, to some extent, conceptually easier to go this way than the other way around, in that it's easier to get a plus sign out of minus signs, and it's a bit harder to get minus signs out of plus signs, if you see what I mean. So that's a bit the idea. And the paradigm, or when I think about phase of matter or systems that can transition between different identities, I immediately think about the fractional quantum Hall effect. So if you're not familiar with it, don't worry, I will give you a very theorist explanation of my understanding, which is basically a description of this picture. So imagine that you have a 2D electron gas. You make electrons flow in one direction, and you plug in a transverse magnetic field that is very, very strong, let's say 20, 30 Tesla, and you measure the Hall resistance here. So typically, naively, you expect, let's say, a linear resistance, a linear dependence of the Hall resistance with respect to magnetic field. And this is indeed what people found in the 80s, but they also found these very flat plateaus in some particular values of the Hall resistance, that they were quantized according to a constant, to a von Klitzing constant, to rational fractions, 1/3, 2/5, and so on, of across the whole plot. Now, it took quite some effort to actually understand what was happening here, and essentially the very, very broad picture painted was kind of surprising, because the quasi-particles that would fit what you would find in experiments turned out to be fractionalized. Fractionalized in that they would have this fractional charge, but more interestingly for me in this case is that they would have these anyonic statistics, right? So they would pick up a phase factor that would make them essentially under-exchange neither bosonic or fermionic, but essentially they would pick up a phase that would essentially correspond to the fraction that you would find in the plateaus. By the way, this has been fairly recently experimentally measured in this another experiment. So my understanding of this plot is essentially that you should expect. This is an Aharonov-Bohm interference type experiment. So you would expect a phase slip that kind of matches 1/3, which is for this particular filling, the type of discrepancy that you expect with normal Aharonov-Bohm interference. Right, so this is the paradigm to some extent, and the mechanism that's at play here is, I would say, in theory, sort of well understood. So you have your electrons or quasi-electrons, and these are effectively low energy dressed with a statistical gauge field, or a Chern-Simons gauge field more generally, that binds to it, and this is this composite that you recognize as a dionic entity that you call an anion, right? So roughly, we wanted to see how 2D is this, or whether you can, think about this mechanism in a more general fashion. So for that, we had to recall a bit roughly how this mechanism works, and this is based on the idea introduced by Frank Wilczek on flux detachment. I think the picture is quite self-explanatory. So imagine a mechanism, or God essentially introducing some flux to this charged particle, to this electron. More generally, the effective picture that you describe is a charged particle orbiting infinitely thin flux tube or an infinite solenoid, right? So it contains a flux phi b. It has a charge q, and you imagine this element essentially forming a gas that for now I consider non-interacting in the sense of contact interactions, but it does interact through vector potential. So each one of these dots and these wiggles around is one of these complexes, right? And I consider essentially a gas of this. I consider initially that these are fermionic entities. They pick up a minus sign under exchange of I and j. Now, what is funny about this is that this is not any vector potential, but it's a very, very peculiar one. It's an Aharonov-Bohm-like vector potential that happens for each of the particles. So if you essentially take the magnetic field felt by a particle at position xi, it's essentially a delta function of the summing over the rest of the particles, right? So this gives you, namely, the flux attachment law, in which your magnetic field is proportional to the density of particles that you have. But now, if you want to know what to plug in here, in this vector potential and essentially solve the problem, well, you have to isolate basically the vector potential. So you have to put the curl to the other side of the equation. And if you do that in the Coulomb gauge, you find something like this. And essentially, this potential decays as 1/r, right? So even though particles don't feel the magnetic field of other particles unless they are sitting on top of each other, they do feel the vector potential, and that's what matters at the end of the day, because it's what couples at the level of the Hamiltonian. Now, what's fun about this is that if you play with this, there's a well-defined transformation, namely what's called a singular gauge transformation that you can do, and exactly transform your eigenvalue problem into some eigenvalue problem in which you remove effectively the gauge field, so you have a free system of particles at the expense of picking up a phase that is essentially the same phase that you find in these fluxes, right? Where this phi alpha beta is nothing more than an argument function, and that measures essentially the angle with respect to some arbitrary reference, the different angle between particles. And this was sort of well known for the fractional quantum Hall effect. What we realized during the pandemic was that there's nothing 2D about this picture, And in fact, you can think more generally that quantum identity in this sense is rather a matter of perspective. All you need to do is to know what to put here. And then anything that preserves number of particles, including 2-body, 3-body, 4-body interaction, as long as they are infinitely short range, this holds true as a essentially glorified Jordan-Wigner transformation that is true in higher dimensions. So just let me briefly mention, there is nothing but a Jordan-Wigner transformation in 2 dimensions. So the object that you put here is not a string, but it's a 2-dimensional surface. So yeah, that's a bit the idea. So just to give you a glimpse of how this works, in 2 dimensions you have a vortex-like vector potential, so the type of flux attachment law that you satisfy is what you expect. Now you have to generalize this notion of synthetic, flux attachment, and in 3D you find something that is monopole-like, and this will give you some funny phenomenology, and in 1D you have something that's proportional to density, and yeah, that's a bit the idea. Now, in terms of applications, well, we can think about anyons in continuum. So you had a brief overview of this. Now I want to go to the Bose case, in which I claim that there's an exact mapping between this Hamiltonian that is sort of Lieb-Liniger-like, so it's a bosonic gas that I will consider later on weakly interacting, but for now just a model. I can put in some trap or something, and essentially I minimally couple it to a gauge potential. So I replace the usual derivative with covariant derivative, and this is the gauge field that I applied, right? So it's an alpha factor, and this is number density. Then I apply my large gauge transformation, which is nothing but the Jordan-Wigner transformation, and I transform it to this other system, such that if I check just this, I would argue this is just a Lieb-Liniger model. But then when I check the commutation relations after applying this transformation, I realize I pick up a statistical factor, and this eta here is just a sign function, right? So you can see this model in this basis or in this basis after or before the transformation, and I think that's it. You might say, okay, so what? Well, you can study what's the phenomenology associated to this model, and check whether you find something interesting, and whether this gauge field give you some features. Yeah. Mm-hmm.
Is the statistics fixed, or is it still a dynamical equilibrium? So do you eliminate it once and you say, okay, I go from boson to anyon with a definite phase?
Yeah.
Or is it more that in time the statistics of your quasi-particle can change?
The way I see it is a matter of perspective. At the end of the day, it's an equality. So the way I think about this is a bosonic system that is dressed with some gauge field. If you prefer to work on the other basis and you want to solve it, let's say, through Bethe ansatz, you can. It's a constant. I consider it a constant, yes. But this, of course, can evolve, and this makes it a dynamical gauge field, similar to what happens in gauge theories, if you're familiar with that. Eta is a sign function. A sign. It takes the sign of position minus the position. So at 0 position, you recover Bose statistics. So that's why it's soft core. So it's only anyonic if when particles are in different positions. And you can check it by just substituting. This is the case, and substituting basically this here. Same is true for fractional quantum Hall effect. Now you can do in the quasi BC regime. So I take essentially weakly coupled system, and I can do Bogoliubov theory, and I calculate the excitation spectrum. And then for alpha 0, of course, you recover the usual phononic linear regime and then the quadratic regime. But as you increase alpha, you essentially get that the spectrum becomes asymmetric, and you get a Roton minimum that softens and softens until it reaches zero energy. And then if you ramp up still more the alpha parameter, the whole thing becomes complex. So there's several features that are interesting. One, the spectrum becomes asymmetric, so that affects essentially the Landau criterion for superfluidity and the how you define speed of sound, depending on whether you move to the right or to the left. And then you can well, yeah, sorry. You can. It's just a.
It should be a unitary transformation to go from one representation to the other.
Sort of, yeah.
So how come it should be the same?
But it's not a normal gauge transformation. It's what's called a large gauge transformation, or a singular gauge transformation that does, in some sense, if you will, what I'm working with is just this model here. I'm forgetting completely about this mapping. This doesn't play a role. It's just an equality that I'm flashing and telling you, look, yeah, if you will, this should be the effect I'm claiming of the statistics that is encoded in this way. But if I think in terms of experiments, what people would have in the lab would be, at the end of the day, a gas of bosons they start with. So I want to check, for instance, what would happen if I just, let's say, were able to implement this as a synthetic gauge field, and I could have control over alpha. That's kind of my thought. And I should be consistent, of course, with what you expect with bosons. I'm making no claims about how to work on this. People have worked, I think, on this, and then they have solved the system. So yeah, now you can think whether you should be surprised about this or not. Well, you find protons and asymmetric dispersion relations in other types of system, namely in dipolar or spin orbit coupled BECs. Now I would like to compare this, for instance, with the excitation spectrum that you expect for fractional quantum Hall effect, in which you have essentially something like a superfluid with a dynamical gauge field. It's namely a Chern-Simons gauge field. And what happens there is that due to Anderson-Higgs mechanism, you gap out the phononic branch, and this is called the magnetophonon, and they call it the magnetoroton. Essentially here, you just don't have this Anderson-Higgs mechanism, basically because you don't have cyclotron motion. So essentially this draws back, and even though you have a dynamical gauge field, this doesn't display Anderson-Higgs. Next thing you can do, for instance, is just do semi-classical dynamics. So imagine this is just Gross-Pitayevsky, and you can imagine preparing a Gaussian wave packet and kicking it to the left in this case. And I would expect some sort of asymmetry if I kick it to the left or to the right. Now, typically, if you do Gross-Pitayevsky, you would expect this wave packet to spread out, and nothing happens even if it bounces back from a wall. If I do this here, I see that it's self-focused, it keeps the shape, and when it bounces back, the solution is unstable, and it dies down as you would expect, right? Now you can check what happens if you kick in the other direction, and here you expect no soliton solution, and indeed you don't find any, but you find this asymmetric expansion that you can explain in terms of an effective Lorentz electric force. Now, what's funny about this is that this was also found in experiments in the group of Laetitia Taruel in 2022 in this beautiful paper, and they indeed managed to prepare this soliton, and they precisely do this thing where they bounce back. There's some compression, and then essentially the whole cloud expands as you would expect, and same for the asymmetric expansion, and they compare it with the usual case. So, well, once you have that, you have the model, and you can try to test a bit the limits and what other features could you expect naively, and something that you might expect, is that because you have the presence of a gauge field, you have to redefine through minimal coupling the superfluid velocity, and this introduces new terms in the conservation of current as another current, or if you will, the continuity equation. And in fact, you get a term that looks like this. And this is well known in the hydrodynamics literature because it's the so-called Riemann-Hopf term, and this gives you what's called a gradient catastrophe. So essentially, this is a pictorial depiction of a dispersive shock wave. What typically happens is that you have the densest part of a wave packet protrudes forward until it reaches essentially kind of a vertical line, and then there's other corrections to this equation that typically create an oscillation, and maybe they lead to solitons or other effects. And if you ramp up the nonlinearity, alpha here, you find the following. So now you have this spitting out of these two solitons. We can ramp it up to 3 or 4, and when they bounce back, they may interact a little bit, but essentially they preserve shape and they get destroyed upon back reflection. And essentially, if you play it slowly, you can see essentially this sharpening on the right-hand side and this massive gradient on density appearing on the right-hand side, and then the spitting out of the soliton at a larger velocity than the original kick. Is there any question? No? Yeah? Couple? What? I assume an initial momentum kick that I imagine it's done through phasing printing or something like that. There's no depth to it. Yeah, sorry. No, it's the Gross-Pitayevsky. It's a Schrödinger equation, yeah. I'm assuming we're doing semi-classical dynamics, and I'm just writing out if I have my Hamiltonian, I can write a Lagrangian, I compute the equations of motion, and I put that I just numerically simulate that with an initial condition that is a wave packet that I kick. There's 0. No, it's 0. Yeah. Okay. Yeah. So in that sense, a bit different to the usual thing that you expect. We also thought, okay, maybe if we run the previous simulation and the other side a little longer, maybe I expect something upon back reflection, and you do have this oscillation, this modulation in density that seems to be there. At some point, it doesn't grow, and it stays there for a rather long time. We are still not sure of what this is. We checked that this is not some numerical issue, and it seems to be there for a range of couplings and just playing around with the simulation a little bit. So that's it for application. Just to finish, just this, you can argue more in general how robust is this idea. Now, this sort of philosophy, in a sense, works also on the lattice. There have been some experiments on this anion Hubbard model in the lattice with bosons in the group of Marcus Greiner, and they do find results that's to some extent consistent with this general picture, in which you have a quantum walk, and you have a drift depending on the value of this gauge field that now shows up in a density-dependent pi-RL phase. They also found these two particle bound states that they are also chiral, and they make them back reflect, and they essentially the bound state is dissolved upon back scattering. We also have some ideas for how to get anyonic vortices in 2D in a pancake-like BEC. And in 3D, you would expect something that is an analog of a Laughlin quasi-particle that is dionic. So it's essentially an electric charge, right? Or where the density nucleates flux, but flux in 3D essentially gives you a source of magnetic field. So you do expect what people call dions arising there instead of solitons or vortices. And with this, I would like to conclude. So I would argue that there is a general mechanism to, in this sense, transmute to some extent the statistics of particles, of matter, and essentially this is encoded in a Jordan-Wigner-like mapping that you can generalize to higher dimensions. This is typically what's called a disorder operator. This is typically just an order operator, and all you need is to find the adequate statistical gauge fields. So we started with this picture of bosons and fermions, and I like to maybe convey this picture of barren composite particles or matter that are linked together. So with this, I would like to thank collaborators at ICFO, Harvard, and of course my former supervisor Patrick at Harriet Watt, and thank you all for your attention.